Welcome. Today I want to give you an introduction to algorithms with a focus on efficiency. So how fast is our algorithm, and in particular, how can we analyze how fast the algorithm is? And we're going to do that by the example of linear search. But let's first have a look at what's an algorithm and where do we use algorithms. We use algorithms in everyday life. For instance, when we do route planning. So route planning essentially boils down to finding shortest path and using a shortest path algorithm. Searching the internet. Information that we're searching will have been heavily pre-processed using sophisticated algorithms. When we analyze data, we also use dedicated algorithms for that. For instance, clustering algorithms, or for classification nearest neighbor algorithms. So we use algorithms for all kinds of things every day, and also on all kinds of devices. So we're not only using algorithms on a computer, but for instance, in the route planning setting, in the car, or on the smartphone, and so on. So algorithms are everywhere. But what is an algorithm? So let's first start with this somewhat kind of general definition, saying that an algorithm is a well-defined computational procedure. So well-defined meaning that it is clearly specified what it does, and it takes some input, so some value or set of values as input, and produces an output based on that. That's an algorithm. In short, we look at algorithms as sequences of computational steps that go from the input to the desired output. And when we talk about algorithms, we very often have to talk also about data structures. So when we want to have, in particular, when we want to have fast algorithms, we often have to think about how do we store the data so that we can allow those fast algorithms. And a data structure is simply the way that we store and organize the data so that we can efficiently perform the operations that we want to perform, also modify the data. And when we talk about data structures, we like to separate functionality from the actual implementation. So the functionality, that's what we call then the abstract data type. So that just says, okay, these operations we want to support. And then the implementation realizes those operations and tells us how are we storing the data, but also how are we implementing the operations? What are the algorithms that implement these operations? Today, we're not going to talk about data structures, but very often when we have algorithms, we also have to think about the data structures. So that's why that's here already. Back to algorithms. What do we expect from an algorithm? So with an algorithm, we want to solve a computational problem. So for starters, this computational problem will have to be requires a well-specified input and output. What do I mean by that? Let's take an example. Here's a problem. Is that well specified? Given a collection of values, find a certain value x. So that in several ways is not well specified, both in terms of the input and the output. So in terms of the input, a collection of values, okay, you might also ask what kind of values, but first of all, the question is also what kind of collection. A common way to store data would be in an array. So here you see an array. What is an array? It's a sequential collection of elements. So we have these elements in sequence, so we can count them 0, 1, 2, 3. So they're stored in such a way that we have constant time access to an element via its index. So if you tell me I would like to have the element with index 5, then in constant time your array can tell you that's 12. Okay, so that's a way to store data. This comes close to what a Python list is. So later in the course we're actually going to see how arrays and Python lists exactly relate, but for now you can think of them as being very similar. So that's how we're given the values. Also, x should be part of the input. But then there's also this issue with the output, as in this statement doesn't even tell us what the output is. It just says the algorithm finds something. But what does it with after finding something? Does it return anything? Does it return x? Returning x is not very useful because we already inputted x. I mean, that can't really have been what we were looking for. What we really want to know is where is x in the collection? Or first of all, actually, whether x is in the collection. And then if x is not in the collection, we also need to return something. So this is now a well-specified input and output specification for the problem we wanted to define here. Give an array A of elements together with an element x. We want to output either an index I such that the element at that index is x. So if x is 12 in this case, I would want to get as output 5. Or if that element doesn't exist, it should report, the algorithm should report that it can't find that element, or more specifically that that element is not in my array. Okay, I wanted to talk about what do we expect from our algorithm. So far we just know what we said what a computational problem is. What do we want from an algorithm? Essentially, there are two things that are most important to us. The first is maybe even too obvious, but very important and something that we always have to carefully check, in particular for more complex algorithms, and that is that this algorithm is actually correct. So given an input, does it give the correct output? Of course, okay, if the algorithm isn't correct, it's not really useful no matter how fast it is. Secondly, the algorithm should use resources efficiently. So let's first briefly talk about correctness. So an algorithm should produce correct output. Of course, there might be settings where it's not clear what that means. So for instance, in the route planning setting, I mean, I could say correct output is if the travel time is actually shortest, but that depends on how the traffic would actually be. So without all the input, I won't be able to produce that output. Also, there might be problems where it's not even clear what the correct solution is. So here, if I want to do character recognition, okay, it looks like an S, but how do I know? The problems that we're going to look at, there we will always have a clear, correct solution. So you don't have to worry about these cases above. Whatever problem we're looking at, there it is very clear what the correct output is. For instance, if I say I want to have the index of an element in an array, it's clear that what it means to give back a correct index. As a side remark, not all types of algorithms focus on being correct all the time. So for instance, randomized algorithms, you can ask for algorithms that are correct with high probability, or approximation algorithms where you say, okay, you don't have to have exactly the correct solution, but it should be close to it. For instance, you don't need to have the shortest path, but a path that is not much longer than the shortest path. But again, those are not algorithms we're focusing on here. We are going to focus on algorithms where there is a clear correct solution and we aim to get that correct solution. So much about correctness. Efficiency. An algorithm should use resources efficiently, and that could mean many things. Our focus is on time. So the next most common aspect to look at is memory. Obviously, memory efficiency is also important. I mean, if you're time efficient, then at least to some extent, often you're also memory efficient because you cannot use more memory than you're spending time. But sometimes, if you're not that time efficient, you also have to look at memory. Our focus is on time. And then there are also other resources like network bandwidth, which for depending on the setting of where you are developing your algorithm, might be very important. And then that's a resource that you should be analyzing. So since we're focusing on time, the question is, how do we measure time? And the natural first idea might be to say, let's implement the algorithm and test it and see how fast it runs. So let's have an example for that here. So what I did here was I was testing how fast can I test whether an element X is in a certain collection. Let's call that collection A. And what you see here is a plot where on this axis you have the size of A, and on the other axis the running time. And then depending, so this is actually more data structure question nearly, or not only nearly, it's a data structure question. Depending on how I store my data, whether it's a Python list or a Python set, and you don't need to know what that is right now. It's just two different ways to store data for the purpose of this slide. We get very different running times. So one looks more linear, one looks somewhat constant. But I mean, I can also only say it looks linear and it looks constant, and it is this, or seems to be this for these specific inputs. But I have to be careful when I want to generalize this. And okay, so this is a useful type of analysis. This is not what we're going to do, because it is difficult to make general conclusions from these types of experiments. So one problem is, in many ways, the running time depends not only on the algorithm. So the running time of experiments is not only on the algorithm, but on lots of factors that have nothing to do with the algorithm. For instance, a computer system, also the programming language will have a huge impact on how fast your algorithm runs, the compiler, my skill as a programmer, whether there are other programs running in the background, and so on. Also, the running time that I'm measuring will very much depend on the data sets that I'm testing. So the statements that I'm making are really just about that data set. So instead of doing experiments, we are going to focus on a mathematical analysis of the running time. And this analysis will have two components. So for one, we're going to look at the running time as a function of the input size. So we're saying, okay, the running time is a function t of n of the input size. And then we're focusing on a specific aspect of that function, and that is the growth rate. This in particular means I'm really just looking at the dominant term. So I want to say something like, okay, the running time is constant, the running time is linear in the input size, or quadratic, whatever it is. Let's take an example. And let me say, we're not going to count machine cycles beyond this slide. It's just, for this, at this point, a good way to formulate what time might be. But we're not going to do that later. Anyway, let's say I have an algorithm A. It needs 50n plus 125 machine cycles to search a list. Then, first of all, we can observe that the 125 doesn't really matter for large data. I mean, already, if for instance, n at the point where n is 3, 50 times 3, 150 is already larger than 125. At the latest, when n is 100, the contribution of the 125 will be very minor. So what I'm really interested in is the linear growth of the running time here. And I'm also not so much interested in the 50, because the 50 again might depend on all kinds of things. In particular, in terms of running time, if it's really time, it will depend on the programming language, or it will depend on the computer system. While the n is really something that comes from our algorithm. So let's take another example. Here we have another algorithm with this running time. If I'm focusing on the order of growth, I'm looking at the dominant term, and I'm going to ignore the factor in front of it. So I take the dominant term, that means I'm ignoring the quadratic term, the linear term, the constant term, and from the dominant term, I'm also just interested in this n cubed, not in the 20. So this algorithm grows, so T of n grows of order n cubed. We want to compare growth rates next by some examples. For that, we have to look a bit more at different types of functions. So let's do that. Logarithms often show up in the context of algorithms. Let's say I take the logarithm of n to the 35. How does that compare to square root of n? So the logarithm is the inverse of the exponential function. So just as we know that the exponential function goes very fast, the logarithm actually goes very slow. And even if I take a high exponent, eventually something like square root of n will be faster. So this will be growing faster, will dominate any logarithmic terms. So generally speaking, logarithmic functions grow slower than polynomial functions, making this more formal. No matter what a is here and no matter what b is here, as long as both are positive, log a to the n grows slower than n to the b. Likewise, if I'm comparing polynomial functions with exponential functions, there it might be more intuitive. Exponential functions grow faster, even if I have a high exponent here in the polynomial function. Now, polynomial functions grow slower than exponential functions, or formally speaking here, n to the a grows slower than b to the n for any positive a, okay, and b larger than 1, because if b is smaller than 1, actually this is not a growing function, but it goes to, if it's between 0 and 1, it will go to 0. And since we've been speaking about logarithms here, just as a reminder, in this class we're going to use logarithms quite a bit, and there are these rules about logarithms, which you know, and I don't want to go into detail here, but you can, if you want to look at them again, pause the video. The only important thing to note here is that if we are talking about logarithms, we're always going to talk about logarithms base 2. And that comes from the fact that in terms of in computer or in the analysis of algorithms, it's very often the base 2 logarithm that is relevant. Good. So I want to put that into use in a quiz soon, but let me first wrap up a bit more further. When we describe an algorithm, so we talked about requirements. So when we now describe an algorithm, these will also be the aspects that we're focusing on. So a complete description of an algorithm will have 3 components. One is the algorithm itself, so a kind of description of the algorithm. And the description will be in whatever way is clearest and most concise. So if I'm describing an algorithm in the context of this course, doesn't have to be an implemented algorithm. So you don't have to give me code. It can also be simply a description in English. It can be code, but there you have to be careful that it's really readable. And readable code, so we're going to see this concept of pseudocode, which is a kind of a mix of, I mean, it's not really just natural language, but it's kind of code using natural language. Or actual code, in particular Python code. I mean, in many programming languages are not very readable, but Python is. So that is, as a description, very often fine. But if you describe an algorithm using code, very often you will want to have at least some kind of high-level description of what the algorithm is doing in words additionally to the code. So that's number 1, the description of the algorithm. Number 2, we want to prove that the algorithm is correct. And we're going to look at that not today, but later in the course. And we want to derive the running time. And that's what we're going to focus on in the remainder. Okay, I promised you a quiz. Let's have a quiz. Namely the following. We're looking at growth rates, and you should order these functions by growth rate, starting from the smallest. So take your time for that and then decide which of these answers is correct. For instance, A would say F is slowest growing, then comes I, this function, H, and then G. So the correct answer is C. So why is that the case? So F is a logarithmic function. All of the other functions have polynomial terms. So we said logarithms grow slower than polynomial functions. So F comes first. I and H actually have the same growth rate, namely n squared. For the growth rate, we look at the dominant term. And the dominant term, I mean, here obviously is n squared. Here also is n squared because logarithms grow slower than polynomial functions. Then G actually has an even larger growth. Now, why is that the case? Because, so here we had for H we had a plus here, but this is times, which means that this actually grows faster than n squared, namely by a term log n. So the dominant term here is n squared log n. While for H, the dominant term, because there was a plus, is simply n squared. And you have more of these types of examples in the practice exercises. So there's lots of material to practice comparing functions, also working with logarithms. Next, we're going to look at algorithms for searching an array and the efficiency of these algorithms. So the input is an array. We have also the size of the array and another value x, namely the value that we're going to want to search for. And the output will be either an index I such that the value at I is x, or not found if x is not in A. So that is our input and output specification. So when we give an algorithm, we should clearly state what is the input, what is the output. And then we have the algorithm as such below. So, and it works on an array. And let me say that we are always going to have arrays that as first index have a 0. So, and why am I doing this? I'm doing that because also in Python, and we're going to use a lot of Python, the first index is 0. Also in C++, the first index is 0. In Java, the first index is 0. So it seems like a logical choice here. In the textbook, since normally we start counting with 1, also the first index is always 1. So that's why our algorithms will look slightly different than in the textbook. But in my experience, starting with 0, in particular if you do also a lot of programming in Python, will be kind of more natural for you. So that's why we're doing that. Okay, that's just a side remark. So the input is given an array. So how can we do linear search? Here is a possible solution. We're also going to see another one. So what does the solution do? It first of all has a variable answer where we store a value, and the value that we initially store there is not found. And you will see afterwards at the very end the output. So if I say return, it means whatever comes in, that's our output. The output that we're going to, that the algorithm will have, so the return value will be answer. So whatever at that point is stored in answer is what we're returning. Initially that's not found, but the algorithm might change that. Then the algorithm has a loop. Here. And what does that mean? I mean, if you have programmed before, you've seen loops and you've seen for loops. But let me briefly explain that here, what these two lines do. So if I say for each index I from 0 to n minus n, what I'm going to do is I'm going to start with I is 0. And then for I is 0, I'm going to execute whatever is in here. I'm going to execute this line to A. When I'm done with that, I'm going to set I to 1. And I'm again going to execute that line. And I'm going to continue with this until I is n minus 1. Then I still execute this. And after that, I stop. And what does this algorithm do in each of these iterations? It checks whether AI is x. So initially I is 0. I'm going to check whether A0 is x. So let's say x is 12. I'm going to check whether A0, so 35 is 12. If this value, so if 35, if I would have a 12 here, then I would go and set answer to I, so to 0. That is not the case, so if there's an if statement and it's not, this condition here does not hold, I'm not going to do the then part. And you're going to, I mean, when you program, you're going to see these constructions, but I think for now, just reading this should be obvious enough. Okay, so for I is 0, we're not going to do anything except for checking this if. For I is 1, 26, 12, still not the case, and so on. So actually, when I is 5, we're going to have that AI is actually x. So then I'm going to set answer. So for I is 5, I would here set answer to I, so to 5. And then my algorithm would continue. It wouldn't do much more. At the very end, I would be returning answer, and I would be returning 5, and then we would know that 12 is at that index. Let me also show you how this would look like in Python, or a possible way it could look like. So def here just tells us we're defining this function. We're going to call it linear search. It has two input values, A, array A, or here actually we're going to use a Python list, A, and the X we're looking for. We're not going to input N because N we can get from A by asking what is the length of A. So len stands for length here. And then, okay, initially we want to set answer to not found. As value for not found, we're going to use -1. You could also do something different there, but -1 works in the sense that if the algorithm returns -1, I know it's not an actual index because my actual indices are between 0 and n-1, so in particular positive. Okay, and then I have this for loop which runs from, so range 0 to this n means it goes from 0 up to n, not including n. It checks whether AI or the value at I in A is x. If so, it updates answer. Eventually it returns answer. And you see here as an example, if this is my array and I'm searching for 10, it's going to return 0 because I have a 10 here. If I search for 9, in this case it will, so the indices are 1, 2, 0, 1, 2, 3. It will find this 9 here. And in this case, if I'm searching for 8 and there's no 8, it's going to return -1. So far, so good. Once more, in terms of how we talk about loops, so this for tells us that we have a loop that runs over I. The loop is variable I. And the inner part, so the part that we are kind of executing over and over again, that is called the body of the loop. And here, this loop is executed n-1 times. We can wonder, is that really necessary? So you might have already thought about, okay, I mean, if you have thought about how would you implement the search, you might already have wondered, why not stop as soon as we found the value? And indeed, we could do that. So let's call that better linear search because it might be faster. Input and output are the same, but we have a different algorithm, and the algorithm does the following. It runs, again, I have a loop that runs from 0 to n-1. If I find x at index I, I'm then immediately returning that value I, and return, if I have a return statement, it means the algorithm outputs something and stops. At that point, the algorithm stops and returns I, if that happens. Otherwise, if I ran through the loop n times and I didn't return anything, meaning I didn't find x, then I'm going to return not found. So that's outside of the loop. If the loop was unsuccessful, you could say I'm going to return not found. And let me show that again in Python. So again, no surprises here. So we have the same for construction and if statement. And at the very end, outside of that loop, if we didn't return in the loop, we're then returning the -1. And again, there are some examples. So what have we seen so far? We've described algorithms. So we wanted a description of our algorithm had 3 parts, and we have this description of the algorithm as such. We wanted to prove correctness also and derive the running time. And deriving the running time is what we're going to focus on next. Let's have a quick quiz. If x occurs several times in the array A, the algorithms that we've seen, which index do these algorithms actually return? So are we getting the index of the first occurrence of x, or does linear search give me the index of the last occurrence and better search the first occurrence? Or does linear search return all occurrences, but better search actually only the first? Or do both of them return all occurrences? The correct answer here is B. And the reason is, so the linear search that we had, it always ran n-1 times through the loop and it went through the array from start to finish. So the last time it found x, that's the I that it kept. That's why the linear search is going to return the last occurrence. While the better linear search, as soon as it found one, it stopped. So that one is going to return the first occurrence. So now let's talk about efficiency. So what we want to do is we want to analyze the running time t of n as a function in n, the input size. And we're interested in the growth rate of t of n. The order, we're focusing on the order of growth. So let's take linear search as an example. What can we say about the running time? First of all, what can we say about the input? So we want to have the running time as input as a function of the input size. So this is the input. The x here doesn't really matter, or we assume that it doesn't matter. The n doesn't matter. Really, what gives me the input size is the size of the array. If the array has size n here, then that is actually what we can use as input size. So we're looking at the running time of linear search depending on the size of A. So when I talk about running time, we also have to think about which input are we actually using. I mean, we're saying we have an input of size n, but there are many inputs of size n. So we could be looking at the input which is where the algorithm runs fastest on. That of course has a disadvantage that it might be fast on this one input, but slow on many others. So this is the type of guarantee that is not really useful. We could try to get an average case running time, which often can be useful, but also is very difficult, and in particular in this setting not really meaningful, because we don't know what we're taking the average over. So if we want to take an average, we need some kind of distribution. There's no reasonable distribution that we can assume here. So what we are going to look at, and what we typically look at, is worst case running time. Meaning, I look at all possible inputs of size n, and whichever is kind of makes the algorithm slowest, that's what is going to determine what t of n is. So the algorithm has worst case running time t of n if for all inputs of size n, the maximum number of, okay, now it comes back down to what are we actually measuring if I want to measure time. What we're going to measure is elementary operations. So the maximum number of elementary operations should be t of n. And by elementary operations, we mean operations, basic operations that run, for which we can assume that they run in constant time. For instance, if I add two numbers, that doesn't depend on n at all because it only involves two values. Subtracting, multiplying, all these kinds of operations. If I copy a single number, I can do that in constant time. Obviously, if I copy a whole array, that is a different story. That takes longer. Also checking an if condition, if again in the if condition I'm just testing an elementary operation, constant time. So these are elementary operations. So that's kind of what we're going to count to measure time. So let's count elementary operations in the case of linear search. Okay, and for that, let's assume that a certain operation I will take ti time. And because it is an elementary operation, that will be independent of n. So line 1, I set answer to not found, so that's an elementary operation, takes t1 time. Then here, line 2, there is actually things happening in line 2 because I initially set I to 0, then I set it to 1, then to 2. But so in one execution of that line, I'm incrementing I by 1. And then I'm testing whether I is smaller or equal to n minus 1 or smaller than n. So we have a test against n. Let's say it takes t2 prime time. We're increasing I, that also takes some time. Then in the body of the loop, we're doing this test, which takes some time. And then if we have to set the answer, that again takes time. And returning also takes some elementary operation. This already looks quite complicated. Let me also point out that my slide says how not to do efficiency analysis. So this is kind of how you might be doing this from scratch, but we're going to see a much simpler and elegant way to do this analysis without all of these T's. But this is just to kind of get started. Okay, so if that is what we're getting, then I can kind of derive lower and upper bounds on what the running time might be, simply by looking at how often are these operations executed. So T1, line 1, I only get once. Then testing I against n, I actually do n plus 1 times, because what happens is each time I start the loop, I'm testing it against n. And when the value is n minus 1, I'm executing the loop. Then I'm going to increment I, and at that point I'm going to notice that I'm beyond n minus 1. This is n plus 1 times, but you can also simply think of it as n times. That is just as fine. This we're going to have n times, this n times. Setting the answer will be between 0 and n times, and this will be once. So overall, this gives me as a lower bound. Okay, if I set this to 0, I get a 0 here, or an n if I have to set the value over and over again. And if we now look at what is happening here, then I can put some terms together. I mean, you have an n. In the first line, this n is missing. Adding all of that up, I get this coefficient before the n, plus lots of constants as lower bound, which is some kind of c1 times n plus d, and a similar upper bound. And again, this looks complicated, and we can do that in a simpler way in a moment. Because what we really just want to know, I mean, we're interested in the growth rate. We're not interested in C1 or C2 or how big D is. What we want to know is the n. What we want to conclude is that the growth rate is n of order n. On of order n, we would write that as theta of n, and that is enough for us. So what is theta of n? And that actually has a mathematical definition, and the definition is as follows. Let g of n be some function from the natural numbers to the natural numbers. Then theta of g of n, and remember what we had seen on the previous slide, what I wrote was theta of n. So in this case, g of n is n, but we can do this for general g of n. That are all functions, and that are all functions f of n which have the same growth rate as g of n. So g of n is n, and theta of n is all functions with linear growth rate. And how is that formalized? It is formalized as stating there are positive constants c1 and c2 and an integer n0, such that f of n can be sandwiched between c times g of n and c times g of n, c2 times g of n, starting at n0. Theta of g of n is a set of all functions that go as fast as g of n. And how this might look like is like this. So f of n in this case, assuming f of n stays between these two green functions, is in theta of g of n. And here you also see the role of n0. It's enough if it's true starting at some n0, because we're really interested in large n. So it doesn't matter that f of n does something weird here. And we write this, so if f of n is in theta of g of n, we're going to write it as f of n equals theta of g of n. That's a bit of an unusual notation, because in principle f of n is an element of the set, but we're writing it as f of n is equals theta of g of n. And again, why are we interested in growth rate? So n squared divided by 4 plus 100n plus 50. That is in theta of n squared. And what we see is if n increases, eventually the quadratic term, let's say for n is 2000, the quadratic term is already 1,000,000, while the linear term and the constant term are still tiny. Okay, so we have an intuition of what growth rate should be, and we have a definition of what growth rate is. Let's look at some more examples that show us that the intuition and the definition actually match. So if you look at 19n cubed plus 17n squared plus minus 3n, what we're saying, we're interested in the dominant term, n cubed, and we're not interested in the coefficient. So the growth rate of this function should be n cubed. So it should be in theta of n cubed. Let's check whether that matches this definition. So as a small quiz, let's assume I want to prove that this function is in theta of n cubed. For that, I need to, so it says there exists positive constants, which means that to prove this, it's enough to show that these constants exist and that with those constants, this formula works out. Let's assume I'm picking n0 is 1. How should I choose C2? So C2 is here. Is 1 a good choice? Is 17 a good choice? Is 19 a good choice, or 36? The good choice here is 36. Actually, we could take any number that is even larger than 36. actually, we might be even able to take a number that is slightly smaller. But these numbers, A to C, those won't work. So why is 36 a good choice for C squared? What I'm essentially saying here is that I'm going to bound this function by 36 times n squared. So why is this function smaller equal 36 times n squared? So let's prove our claim using a mathematical proof. In a later lecture, we're going to look at mathematical proofs in slightly more detail. But here we're simply kind of we're going to see a first mathematical proof in this lecture for this claim. And okay, our choice will be, we're choosing C1 as 19, C2 as 36, as I kind of said, I would, N0 as 1. So what do we have then for all n larger equal N0? So let me start. So I want to have 0 smaller equal C1 times g of n in this case is n cubed. I want that this is smaller equal f of n. So this is, I mean, and it's definitely, I mean, C1 is 19, so this is not only smaller equal, but it's equal to 19 n cubed. And now this is smaller equal 19 n cubed plus those remaining terms. Why is that the case? Because 17n squared minus 3n is positive for all n. And you can see that by the fact that n squared is larger equal n, 17 is larger than 3, so 17n squared, the product here, is larger than 3n. So, but that is already f of n. Now I want to prove that f of n is smaller equal C2 g of n. So f of n conveniently is smaller equal, actually smaller than 19n cubed plus 17n squared. I mean, I dropped the negative term. This only makes the function larger. So this is smaller equal 19n cubed plus 17n cubed, because adding a factor n here just again makes the function larger. But this is actually 36n cubed, which is C2 times g of n. Let me write it as n cubed, which is exactly what we needed to show. Let me write it down again. 0 is smaller equal to 1 times n cubed, which is 19 n cubed. Then those remaining terms, because 17 n cubed is 17 n squared is larger than 3n, is an upper bound. Then raising this, taking an additional factor n here, also makes it just larger. And this is our proof that this function here is in a theta of n cubed. So let's look at a different statement, again involving this function here. Namely, I mean, we said that growth rate is n cubed. In particular, it is not n squared. And that's, let's say we want to show that the growth rate is not n squared. How would we do that? So this is actually a so-called proof by contradiction. So we're going to assume that this is true. We're going to see that a proof will output nonsense. And from that, we can conclude that our initial assumption was wrong. What we're going to do is a proof by contradiction. We assume that we assume that there is C1, C2, N0 larger 0, such that 0 smaller equals C1 n squared plus is smaller or equal 19n cubed plus 17n squared minus 3n, which is smaller or equal c2 n squared. Now you can already think about which part of the statement is nonsense. The part that is nonsense is the second equation, inequality. And why is that the case? What does that tell me about C2? So let me first say that this is larger or equal 19n cubed plus 17n squared minus 3n. That is actually larger or equal 19n cubed. So we had that argument on the previous slide. What we now have is that 19n cubed is smaller than c2n squared, which in particular means that 19n, this implies that 19n is smaller or equal c2. But c2 is a constant while n goes to infinity, so this is not possible. So the statement that this is true cannot be the case, so this claim actually holds. So once more, we assume that we actually have that this is in n squared. We take the corresponding constants, we lead this to a contradiction, and then we know that this cannot be an equal, or that this function cannot be in n squared. Good. Going back to linear search, what does that mean for us? So actually working with all of those TIs, was much too tedious. Instead, we're going to say that all of these elementary operations take constant time. We can write constant as theta of 1. We're also going to see O of 1, but that will be in a moment. So what we then would be doing is we would be say, okay, line 1 takes theta of 1 time. Line 2, as such, the operations take theta of 1 time. I execute them n times. Line 2a is same. And line 3 is again 1. So and if I add all of those terms up, so here I have this twice here, I just wrote it once. That doesn't matter because factor 2 doesn't matter. So the lower bound is theta of 1 plus theta of 1 times n plus theta of 1, which is simply theta of n, because this term dominates. The upper bound is the same. So I know it is in theta of n. Much simpler, no of the TIs involved. For better linear search, let's have a look at that also. So what is the running time of better linear search? So the crucial question here is, how often is 1a executed? And that is different for the worst and the best case. So in the worst case, x is not in A, and then we still search the whole array to notice that. So then the running time is linear. But in the best case, I immediately find x, and then the running time is constant. So what we can say here overall about the running time is that linear is an upper bound, and upper bounds we're going to express by this notation of O of n. Yeah, so whatever I'm comparing to O of n, so T of n, let's say I'm saying T of n is an O of n, then I'm saying the running time is at most linear. How is this formally defined? This looks very much like a theta, just that we here only have the upper bound. So we want to have a positive constant c and n0, so that we can bound f of n by c times g of n for large enough n, so larger than n0. So O of g of n are all the functions that go at most as fast as g of n, so that are upper bounded in terms of growth rate by g of n. So this is how that looks like in terms of graphs. Again, we can ignore everything smaller than n0, but then at that point, for a suitable constant c, g of n should grow faster than f of n. And the notation that we use here is again with the equal sign, where we say f of n is, we read it as f of n is an O of g of n, but we write that equal sign. The O of n notation we use for upper bounds. Running time is never worse than that given function. Then we also have lower bounds. So we want to also be able to express that the running time is never better than a given function. And lower bounds we're going to write by using omega. Omega gives lower bounds, so we can say better linear search always takes at least constant time. Okay, that is not very interesting. Any algorithm takes at least constant time. But that we express by saying that it's in omega of 1. And formally, this is very similar to O of n, just that we have c times g of n as a lower bound here. So omega of g of n are the functions that go at least as fast as g of n. Here's the picture again, ignoring everything smaller than n0. F of n should be above g of n for a suitable constant c. Notation again is the same. What we have here is now expressions for saying, okay, the asymptotic growth rate is equal, then we use theta. If we have an upper bound, we use O. If we have a lower bound, we have omega. So let's have a small quiz about this. How many of the following statements are true? So have a look at the statements, count how many are true. So 4 of these are true. And let's see that by going through them one by one. So 50n plus 150, is that in O of n squared? So growth rates are different, but O expresses an upper bound, and n squared is an upper bound for 500n plus 150, because here the growth rate is n squared is more, so this is true. 4n log squared n plus 20n is in theta of n log n. True or false? This is false. Why is it false? Because here the dominating term, we have the n log squared n, but there's an extra log factor here compared to the log n. Yeah, so because this is a product here, which is larger than this, and theta would ask for same growth rate, this is a false statement. Then, is n log n in omega of n? That is the case because omega expresses a lower bound and n is a lower bound for n log n. Or sufficiently large n, meaning n at least 2. So this is true. N to the log squared n is that in O of n to the 4 thirds. That's a tricky one. To compare those, I mean, let's divide both by n. What we get then is actually that we're comparing log squared n with O of, and if I divide n to the 4 third by n, I keep n to the 1 third, so third root of n. So we know polynomial functions go faster. The question is this polynomial function an upper bound for log squared n? And so polynomial functions go faster than logarithmic functions. This is true. Last one on the list that we had, and we said 4 would be true, so this one will also have to be true. 57 n squared plus 17 log n is that in theta of n squared. Ignore the 52, ignore lower order terms, n squared, fine, is true. Let's have two more statements here. Is O of n a subset of O of n to the 4? Yeah, so I mean, in principle, these O's and thetas, those are sets of functions. So it's a set of functions with at most linear growth rate, a subset of the set of functions with at most n to the 4 growth rate. That is obviously, if I phrase it like that, true. Here's one last one. An algorithm with a worst case running time O of n log n is always slower than an algorithm with worst case running time O of n, if n is sufficiently large. True or false? This is false in several ways. First of all, worst case running time. And always. That doesn't fit together. I only know something about the worst cases, not about, I mean, I know that for other instances, it's upper bounded by the worst case, but it could be that for some input, the one algorithm once in second algorithm, once in linear time, while the first algorithm actually takes constant time. So that's why this is wrong. It's also wrong because I only know O. And everything that goes at most as fast as this fits this description. So in particular, this O of n log n could be hiding a T of n that is of order square root of n. That would be also upper bounded by n log n, but would be lower than something that would be of theta of n. So this statement is false in many ways, and to get an understanding of O's and thetas and omegas in the context of algorithms, it might be good to look at this statement carefully if this was not yet clear. Maybe the next slide also clarifies this a little bit, because here, so this is something that is sometimes confusing. So when should we be writing theta? When should we be writing O? What does it mean if the running time is in theta of n? What does it mean if the worst case running time is in theta of n? So if I say the running time is in theta of n, I mean probably actually mean the worst case running time, but I'm not saying it, so I have to assume I mean the running time in general. Then I would have to have that for all inputs, the running time is linear. In contrast, if I say O of n, then I'm saying for all inputs, the running time is linear or better. If I talk about worst case running time, if I say the worst case running time is in theta of n, then I say for the worst case input, the running time is linear. Which is, so the statement that for all inputs it's linear is actually a stronger statement. So here I'm saying the worst case running time is linear. That might still mean that for other instances, the algorithm is faster. If I say the worst case running time is in O of n, then again, the worst case is bounded by O of n. That means also that for all inputs, it's bounded by linear, because all inputs are bounded by the worst case. So, which of these are we going to use most commonly? So first of all, I mean, there's kind of a relation between these. So if all inputs run in linear time, then obviously the worst case runs in linear time, but not vice versa, and so on. What we commonly focus on is simply getting an upper bound on the worst case, or an upper bound which is an upper bound on all instances. Meaning that then we very often just say something about the O. The reason being twofold. One, having an upper bound is very useful. It's maybe less relevant whether there are instances that are faster or not. Secondly, lower bounds are also very difficult to prove, at least in general. So very often we're going to use O of n. Of course, we have the risk that, I mean, we could be giving an O of n that is too large. So we're always going to try to do the analysis as tight as possible without showing that it is tight. Okay, let's see this once more in the context of better linear search. So here we have all lines take, I mean, the operation as such takes linear time, but I'm executing it n times. Return, I do constant time. Summing this up, so here I have written it as a sum. I get a running time that is in O of n. And of course, there are instances where the algorithm is faster. We could be saying that the worst case running time is theta of n. Despite there being instances that are faster, I can always, for any n given input, which actually takes linear time, namely when x is not present. But for the purpose of the analysis, we will often simply prove the O. And the way we're doing this analysis, which I kind of also showed here again, is we simply look at every line, how long does it take? If we have loops, we think about how often does the loop run, and then we sum everything up and get our result. And this last part here about getting a theta, so that if I'm not explicitly asking for that, you also don't have to do it. So meaning that we're going to use O quite a bit. So that was all for today. Let's quickly recap what we've seen. Were algorithms. And if we have an algorithm, we want to have three parts. The description of the algorithm as such, expressed in whatever way is clearest. Correctness, proof of the algorithm, and running time analysis. We haven't done correctness proof of algorithms yet, so we have to come back to that at a later point, but we have now had a look at running time analysis and how to formally argue about that. Once more about how we're presenting algorithms, it should be presented for a reader and not for a computer. And that you should keep in mind when you give the algorithm. So it is fine to not give code, but simply natural language in the context of this course, unless I ask you for Python code. It should be clear what the input and output are. It should be clear what the various variables are that you use. And you can use code, and I would actually recommend to also use Python code when possible, because it also for you clarifies the algorithm, but also make sure that on a high level it's clear what your algorithm does, and that you typically do with some kind of high level description. And we've seen how to analyze with O's and thetas and sometimes omegas. And again, what I just said a couple of slides ago, very often we're going to use O because very often we just want to make sure that we have an upper bound. When you kind of asked to give an algorithm with a specific running time, so let's say I ask you, give an algorithm that runs in linear time and solves the following problem, make sure that the analysis fits your algorithm. So, I mean, if I ask you for a linear time algorithm and you give me a quadratic time algorithm, that is not ideal, but it is even worse if you give me a quadratic time algorithm, but try to prove that it runs in linear time. So if you have a quadratic time algorithm, then obviously the running time analysis should also figure out that the running time is quadratic. So that's all for today. Next time, we're going to look at mathematical proofs a bit more.